Picture a piece of hardware that almost nobody thinks about. Not a phone, not a laptop, nothing with a screen anyone would ever touch. A robotic float, roughly the size of a fire extinguisher, drifting somewhere in the middle of the Southern Ocean. It has no engine in the conventional sense. It changes its buoyancy, sinks to 2 kilometers, drifts with the current for 10 days, then rises back to the surface, measuring temperature and salinity the entire way up. Then it transmits its data to a satellite and sinks again. There are roughly 4,000 of these floats scattered across the world's oceans, part of a network built so that no single anomaly could ever be dismissed as a glitch in one machine. In the early months of 2023, hundreds of them, independently, without any coordination beyond shared engineering, began reporting something with no precedent in the network's recorded history. Not a record close to the previous one, not a value nudging the upper edge of what had been seen before, a value so far outside the known range that the scientists reviewing the data initially treated it as a calibration error. It was not an error. Satellites measuring sea surface temperature from orbit were showing the same thing. Weather balloons launched twice a day from hundreds of stations across every inhabited continent were showing related anomalies in the lower atmosphere. Sea ice sensors around Antarctica were recording an extent so far below anything in the satellite record that some researchers initially assumed a processing fault in the algorithm. Multiple independent observation systems, built by different countries, calibrated against different standards, maintained by people who had never spoken to each other, were converging on the same conclusion at the same time. Something had shifted, and it had shifted fast. This is not a story about a single broken record. Individual records happen constantly in a system as large as the planet's atmosphere and ocean. There is always some station somewhere registering its hottest day or its driest month. What makes 2023 and the years that followed different is the word simultaneous. When several independent measurements of a complex, interconnected system cross the boundary of their documented variability at the same time, that is not noise. That is a signal. The question here is not whether the signal exists. The data on that point is no longer seriously contested. The question is what the signal means, how it got generated, and what it implies about the years still ahead. To understand any of that, it helps to start with what the atmosphere actually is, not in the textbook sense, but in the functional sense that matters here. The atmosphere is, at its core, a heat engine. It receives energy from the sun, mostly concentrated in the tropics, where sunlight strikes the surface most directly, and it spends its existence moving that energy toward the poles, where it eventually radiates back into space. Every wind, every storm, every monsoon, every blizzard is, in one way or another, a byproduct of this transport process. How efficiently the engine runs depends on a single defining variable: the temperature difference between the tropics and the poles. A large difference drives strong, organized circulation. A small difference produces weaker, messier, more erratic transport. This variable is currently shrinking, and in one direction only. The Arctic has been warming at roughly 3 to 4 times the global average rate for decades, confirmed by multiple independent observational records stretching back to the 1970s. It is not a model projection. It is a measured fact. The consequence follows directly from thermodynamics, As the gradient narrows, the engine's transport efficiency declines. This is not a side effect of climate change. It is one of its central physical mechanisms, and understanding it matters because nearly everything described in the rest of this account traces back to that one underlying shift in how the planet's thermal engine operates. It helps to think of the atmosphere as a stack of distinct physical regimes rather than a single uniform gas envelope. In the lowest 12 to 15 kilometers, the troposphere, virtually all weather happens. Temperature falls with altitude, air mixes vertically, clouds form, rain falls. This is the layer every person who has ever lived has spent their entire life inside. Above it sits the stratosphere, extending up to roughly 50 kilometers, where the air is thin, vertical mixing essentially stops, and the ozone layer absorbs most of the sun's ultraviolet radiation. The stratosphere has no weather in the conventional sense, but it has currents, and those currents influence the weather happening far below through mechanisms researchers have only begun mapping in detail over the past few decades. Above that come the mesosphere, the thermosphere, and the exosphere, each operating under its own rules, each responding to changes above or below in its own way. None of these layers function as sealed compartments. They form a coupled machine, in which a disturbance introduced in one layer can propagate through entirely different physical pathways into the others. This coupling is why an anomaly first detected in the upper atmosphere can show up months or years later as a flood in one country and a drought in another. Let's pause on the catalog of what actually happened, stated as plainly and as carefully as the data allows. Between 2023 and 2024, several independent indicators of the state of the planet's atmosphere and ocean crossed thresholds that had never been crossed before in the instrumental record. Global average sea surface temperature reached values with no precedent across roughly a century and a half of systematic measurement, and the size of the jump above the previous record was unusually large compared to the typical step between successive records. Antarctic sea ice extent fell to levels so far below anything previously observed that the deviation, measured in standard deviations from the historical mean, was large enough that some statisticians initially questioned whether the underlying distribution assumptions still applied. Atmospheric rivers and jet stream meanders began behaving with a persistence and a geographic synchronization that had previously shown up only in isolated, individual episodes, rather than as a recurring statistical pattern. Stratospheric water vapor concentrations, elevated by a major volcanic event a year earlier, remained well outside historical bounds, and several long-running cyclical indicators that climatologists have relied on for decades to anchor seasonal forecasts began drifting from their expected rhythm in ways that were not easily explained by any single known driver. 5 or 6 independent indicators, each tracked by a different research community using different instruments, all moving outside their documented range within roughly the same 18-month window. The odds of that occurring through unrelated random fluctuation are vanishingly small. When several independent measures of a complex, nonlinear system depart from historical norms at the same time, the most defensible interpretation is not coincidence. It is that the system has entered a functionally different operating regime. What pushed the system there? This is where the science becomes genuinely uncertain, and where honesty requires presenting candidate explanations rather than a single confirmed cause. Because the research community itself has not converged on one dominant driver. Several plausible contributors have been identified, and the working assumption among most researchers studying the period is that more than one of them acted together, in a system that does not respond to combined pressures the way it would respond to the sum of each pressure taken separately. The first candidate is a change in global shipping regulations that took effect in 2020. For decades, the world's container ships, tankers, and bulk carriers burned fuel with a relatively high sulfur content, releasing large quantities of fine aerosol particles into the air above shipping lanes. These particles, while harmful as air pollutants, had an unplanned side effect on climate. They served as condensation nuclei for clouds, producing brighter, more reflective cloud formations along major maritime routes, visible from space as pale streaks across the open ocean. This was an unintentional, unmanaged form of solar reflection, operating at a scale large enough to matter. In 2020, new international rules sharply restricted the sulfur content permitted in marine fuel, a change made for sound public health reasons, since sulfur emissions are genuinely damaging to respiratory health in port communities. But the climate side effect was not fully accounted for in advance. The reflective cloud trails over shipping lanes began to fade. Ship track clouds became measurably less bright and less extensive within a few years of the new rules taking hold. The ocean surface beneath those routes began absorbing more incoming sunlight than it had previously. Estimates of the resulting warming effect vary considerably across research groups, partly because reconstructing the precise historical contribution of marine aerosols to cloud reflectivity over open water is a genuinely difficult measurement problem. But even the lower end of published estimates is significant at the scale of the global climate system. Crucially, this shift happened quickly, over a span of a few years, rather than gradually unfolding across decades. A masking effect the climate system had effectively treated as a stable background condition for half a century was removed in a comparatively short window. A second candidate traces back to a single geological event. In January 2022, an underwater volcano in the South Pacific produced one of the most powerful explosive eruptions in the modern instrumental record. The shock wave circled the planet and was detected multiple times by barometers thousands of kilometers away. What matters here is not the explosion itself, but what it injected into the stratosphere. Because the eruption occurred underwater, in shallow seawater interacting violently with magma, it lofted an extraordinary quantity of water vapor, not just ash and sulfur dioxide, into the stratosphere. Published estimates suggest the eruption added an amount of water vapor equivalent to roughly 10% of the stratosphere's pre-existing total water content, delivered within a span of hours. Nothing comparable had been recorded since satellite monitoring of stratospheric composition began. Water vapor in the stratosphere is not simply humidity. It absorbs and re-emits infrared radiation. It participates actively in chemistry that affects the ozone layer, and it can alter the dynamics of a part of the atmosphere that had historically been considered comparatively stable and predictable. Researchers tracking satellite data in the months following the eruption observed the stratosphere over the southern hemisphere warming faster than existing forecasts had anticipated, and not because heat was rising from below, but because of processes occurring within the layer itself. The mechanism, a water vapor radiative effect trapping outgoing infrared radiation in a layer that had previously been comparatively transparent to it, was theoretically known beforehand. Seeing it expressed this clearly, this quickly, was something else entirely. A third candidate is simply the ordinary cyclical warming associated with the strong El Niño event, coinciding with this same period and reliably elevating global surface temperatures for a year or two. A fourth is the long-running gradual increase in the atmosphere's greenhouse gas concentration. The slow background trend against which these shorter-term factors were superimposed. None of these candidate explanations are mutually exclusive, and most researchers studying the period describe the 2023 to 2024 anomaly cluster as the product of several of these factors acting in combination, rather than the result of any single dominant cause. What matters for understanding the broader pattern is the way these factors interacted, not which one deserves the largest individual share of credit. In a strongly nonlinear system, two combined disturbances do not simply add together. They can multiply, producing an outcome substantially larger or structurally different from what either disturbance would have produced alone. Several of the indicators that crossed historical thresholds during this period are consistent with that kind of nonlinear amplification. Though attributing a precise numerical share of the outcome to each individual contributing factor remains an active and genuinely unsettled area of research. To see where this combined effect became most visible in day-to-day weather, it helps to travel up to an altitude of roughly 7 to 12 kilometers, where winds can reach speeds exceeding 200 kilometers per hour. These are jet streams, narrow, fast-moving rivers of air that circle the planet in the middle latitudes of both hemispheres. They determine where rain falls and where drought sets in. They steer the storm systems that show up in your weekly forecast. Pilots negotiate flight paths around them to save fuel on transatlantic routes. Jet streams exist for the same reason the entire atmospheric engine exists: the temperature contrast between the tropics and the poles. A large contrast produces a strong, relatively straight jet stream that stays locked in the middle latitudes. A small contrast produces a weaker, more meandering jet stream, prone to deep loops that pull tropical air far north and Arctic air far south. As the Arctic warms faster than the rest of the planet, that contrast shrinks, the jet stream weakens and meanders more, and the loops it forms become deeper. Critically, those deep loops also begin moving more slowly. As they slow down, they can stall over the same region for days or even weeks at a time. This is what meteorologists call a blocking pattern. A blocking high parked over a region in summer is not a 3-day heat wave. It can become a 3-week heat wave. A blocking low parked over mountainous terrain is not a single storm. It can dump several months' worth of rain in a handful of days. Blocking patterns sit behind a disproportionate share of the most destructive weather events of the past several years. This trend itself was not new. It had been described in the scientific literature for years and incorporated into forecasts as a slowly intensifying pattern. What researchers identified as new in the 2023 to 2024 data was a higher degree of long-range coordination between meanders occurring at very different longitudes than had ever been documented before. A phenomenon resembling resonance, in which oscillations in one part of a system reinforce oscillations occurring simultaneously in a distant part of the same system. This kind of large-scale wave resonance had been theoretically predicted years earlier by researchers studying the dynamics of planetary-scale atmospheric waves, on the assumption that it would become detectable only once Arctic warming reached a level beyond what is currently observed. Its earlier-than-expected appearance suggests the atmosphere's sensitivity to a shrinking temperature contrast may be higher than existing models assumed, a finding with implications well beyond any single season's weather. A related, quieter disruption has been unfolding in the stratosphere above the tropics. Since the 1960s, climatologists have tracked a remarkably regular cycle known as the quasi-biennial oscillation, in which stratospheric winds over the equator reverse direction roughly every 28 months, with enough consistency that it functions almost like a metronome embedded in the tropical atmosphere. Forecasters rely on its phase to anticipate monsoon timing, tropical cyclone activity, and the distribution of stratospheric ozone. In 2016, this cycle skipped a beat for the first time in the entire observational record, an anomaly that was thoroughly documented, studied, and ultimately treated as an unusual but isolated event. What followed in the years after 2022 looked different. Rather than a single disrupted cycle, researchers began documenting a change in the amplitude and vertical structure of the oscillation itself, as though the underlying mechanism generating the rhythm, not just its timing, had shifted. There is a meaningful distinction between a clock that occasionally runs fast and a clock whose internal spring has changed shape. The first is a calibration problem. The second is a different problem entirely, one that calls into question how reliable the clock will be going forward. Several research groups studying tropical stratospheric dynamics have linked these structural changes to the same broad set of factors already discussed: elevated stratospheric water vapor, shifting temperature gradients, and altered wave activity in the tropics. If the oscillation's underlying structure is genuinely changing, then a tool relied on for decades to anchor seasonal forecasting across a huge swath of the planet becomes less dependable, exactly where the cost of an unreliable forecast is highest: in regions where monsoon timing determines food security for hundreds of millions of people. There is an unexpected side effect tied specifically to the stratospheric water vapor surge that deserves its own mention because it intersects with one of the most successful pieces of international environmental cooperation in modern history. In 1987, the world's nations agreed to phase out chlorofluorocarbons, industrial compounds responsible for destroying stratospheric ozone, the atmospheric layer that filters out most of the sun's ultraviolet radiation and makes life on the surface in its current form possible. That agreement worked. Chlorofluorocarbon concentrations declined steadily for decades, and the seasonal ozone hole over Antarctica shrank correspondingly, year after year into the 2020s. Water vapor in the stratosphere is not chemically inert. It reacts with residual chlorine compounds still lingering from earlier decades of chlorofluorocarbon use. And in the presence of additional water and the extremely low temperatures found above Antarctica, those reactions can activate chlorine radicals, the same molecules responsible for ozone destruction in the first place. Research published in the years following the 2022 eruption documented a statistically significant temporary reduction in ozone concentrations over specific regions of the southern hemisphere, with a spatial pattern matching the distribution of the additional volcanic water vapor. This is not a reversal of decades of progress under the 1987 agreement, and long-term ozone recovery has continued. But it illustrates something important. An atmosphere already altered by decades of human activity may now respond more strongly to natural disturbances that would once have had a far more limited chemical effect. The relationship between cause and consequence has become more tangled than the relatively linear models of an earlier scientific generation assumed. Once a perturbation like this is introduced into a system, an obvious question follows. Does the system simply return to where it was before? The stratospheric water vapor will eventually settle. The reflective cloud trails over shipping lanes may stabilize at some new equilibrium. Won't things eventually correct themselves? It is a reasonable question, and answering it requires understanding what climate scientists call system inertia. Picture the climate system as an enormous flywheel that has been accelerating for decades. Even if the force driving that acceleration were removed entirely, right now, the flywheel would continue turning for a long time simply because of the momentum it has already accumulated. The single largest carrier of this inertia is the ocean. Water has an extraordinary capacity to store heat, and the upper few hundred meters of the world's oceans have already absorbed the overwhelming majority of the additional energy trapped by rising greenhouse gas concentrations. That heat has not disappeared. It will continue radiating back into the atmosphere gradually over decades. This is sometimes called committed warming, the portion of future temperature increase that is already locked into the system's thermal balance, regardless of what happens to emissions starting today. Even in a hypothetical scenario where all greenhouse gas emissions stopped immediately, global surface temperature would continue rising for several more decades simply to catch up with the heat already stored in the ocean. Ocean inertia is only one layer of this problem. The cryosphere adds another. The ice sheets covering Greenland and West Antarctica are not simply enormous, static blocks of frozen water. They are systems with their own internal dynamics, their own feedback loops, and critically, their own stability thresholds. An intact ice sheet reflects sunlight efficiently, helping to keep the surrounding air cool and the system stable. Once it begins eroding at the margins, darker rock or open water is exposed underneath, absorbing more heat, which accelerates melting at the edges further, exposing still more dark surface. This is a feedback loop that, once underway, can continue advancing on its own without requiring any additional outside push. Glacial outlet streams, the rivers of ice that drain toward the sea, are also undercut from below by warmer ocean water reaching their grounding lines, a process that accelerates their flow toward the coast in a way that can become self-sustaining once a certain threshold is crossed. This is what researchers mean by a tipping point in the context of ice sheets, not the moment melting begins, but the moment at which the dynamics of collapse no longer require continued external forcing to keep advancing. Estimates of how close the major ice sheets sit to these thresholds have generally been revised toward greater concern in recent years. The rate of mass loss observed in Greenland has consistently exceeded the central projections published a decade earlier. Parts of the West Antarctic ice sheet draw particular concern from specialists because portions of its bedrock foundation sit below sea level, a configuration that is potentially vulnerable to a self-reinforcing destabilization process once initiated. Permafrost deserves its own extended treatment because it represents one of the largest and least predictable wildcards in the entire system. Roughly a quarter of the land surface in the northern hemisphere consists of permafrost, ground that has remained frozen continuously for thousands, in some places tens of thousands of years, across Siberia, Alaska, northern Canada, and the Tibetan Plateau. When organisms die in frozen ground, their organic material does not fully decompose because cold temperatures suppress microbial activity. Over millennia, this has created an enormous reservoir of stored organic carbon, with estimates generally clustering around 1.5 trillion tons, roughly double the amount currently present in the atmosphere as carbon dioxide. While the soil stays frozen, this carbon remains essentially inert. When it thaws, microorganisms reactivate, decomposition resumes, and both carbon dioxide and methane are released. Methane matters disproportionately here because over a 20-year horizon, its heat-trapping potency is roughly 80 times that of carbon dioxide. It exists at much lower atmospheric concentrations and breaks down faster, but its short-term warming contribution is still substantial. Measurement stations across Siberia, Alaska, and Canada are recording rising greenhouse gas fluxes from terrain that, 50 years ago, stayed solidly frozen year-round. Thermokarst lakes are forming where the ice in permafrost collapses. Stretches of coastline, once held together by frozen ground, are eroding away. Infrastructure built on the assumption of permanently frozen foundations is losing its footing. This is a feedback loop in its own right. More carbon released, more warming, faster thawing, still more carbon released. Earlier generations of climate models either omitted this feedback entirely or represented it in a highly simplified way. Current models include it, but it remains one of the most uncertain elements of any long-range projection, because the rate at which carbon escapes from thawing ground depends heavily on soil type, the specific composition of organic matter, and microbial community structure, all of which vary enormously across the permafrost zone. This is the point where a discussion of probability becomes unavoidable, because risk management has a basic equation behind it. Risk equals the probability of an event multiplied by its consequences. It sounds almost too obvious to state, yet institutions and individuals consistently misjudge this equation in the same direction. They systematically underweight low-probability events that carry catastrophic consequences, a pattern often described as fat-tailed risk. In an ordinary statistical distribution, the probability of an extreme outcome falls off sharply the further it sits from the average. But in complex, non-linear systems, financial markets, ecosystems, the climate, extreme outcomes occur considerably more often than a simple normal distribution would predict. The tails are fatter than intuition expects. Rare events happen more frequently than the math of an idealized bell curve would suggest. This concern has motivated a serious body of recent research into how different components of the climate system interact, particularly components capable of crossing their own internal thresholds, the tipping points already discussed in the context of ice sheets. Among the systems most frequently studied for this kind of behavior are the West Antarctic ice sheet, a potential weakening or eventual collapse of the Atlantic meridional overturning circulation, permafrost degradation, drying and dieback of the Amazon rainforest, the loss of Arctic sea ice, shifts in the West African monsoon, and the bleaching of coral reef ecosystems. The central finding running through this body of work is that these systems are not independent of one another. They are coupled through ocean and atmospheric circulation, through the planet's radiative balance, and through biogeochemical cycles. And in a number of these pairings, the connection is strong enough that crossing a threshold in one system could help trigger a threshold crossing in another, even without any additional external push, what researchers describe as a tipping point cascade. It is important to state this plainly without overstating it. Under most current trajectories, the probability of triggering a full cascade through several linked tipping points in the coming decades is assessed as low, but not negligible, and it warrants serious attention precisely because the consequences of such a cascade would be extraordinarily large in scale and exceptionally difficult to reverse. Insurance, as an industry, exists specifically to manage this category of risk. Nobody buys insurance against an event guaranteed to happen. They buy it against an event that might happen, where the consequences would be unbearable to absorb without it. A cascading climate transition belongs in exactly that category. A probability that is not high, paired with consequences too large to dismiss. This raises a deeper and less frequently discussed question, one that sits at the boundary between physics and philosophy. Is the system still moving toward a different state, or has it already arrived in one? In the mathematics of nonlinear dynamical systems, there is a concept called an attractor, a state toward which a system tends and within which it remains stable. The basin of attraction around that state describes the range of starting conditions from which the system will return to it if disturbed. Push the system slightly and it settles back, the way a marble rolls back to the bottom of a bowl after a small nudge. But complex systems can have more than one stable bowl, separated by ridges. While a system sits inside one bowl, small disturbances do not dislodge it. If a disturbance is strong enough to push it over the ridge, however, it slides into a different bowl entirely, a new equilibrium. Returning from the second bowl to the first can require a substantially larger push than the one that caused the original transition, a property known as hysteresis, and it matters enormously because it means a transition is not necessarily reversible by applying the same effort that caused it in the first direction. Does the climate system have more than one such stable state? The answer, based on paleoclimate evidence, is clearly yes. Earth has existed in states ranging from near total glaciation to ice-free conditions extending almost to the poles, and several intermediate configurations between those extremes, each persisting for long stretches of geological time. The state in which all of human civilization has developed is itself simply one of these attractors. The open question is how deep the current basin is, and how close to its edge the system has already drifted. Some of the most heavily cited pioneers in climate science argue that the cluster of anomalies observed in the 2020s may represent early signs of a genuine regime shift, rather than simply an intensification of familiar trends. Others disagree, arguing the same anomalies can be explained by a combination of known factors without invoking the concept of a regime change at all. This disagreement is real, and it remains unresolved, not because the question is unserious, but because it is genuinely difficult. The available data is not yet sufficient for a confident answer, and the stakes are high enough that neither side is rushing toward a premature conclusion. The openness of this debate is itself important, because the answer shapes which responses count as adequate. Few systems illustrate the stakes of this question more concretely than the Atlantic Meridional Overturning Circulation, often abbreviated AMOC, the system of currents that carries heat from the tropical Atlantic northward. Warm, salty water travels along the surface toward high latitudes, cools, becomes denser, sinks, and returns south as a deep current. This circulation functions like an enormous pump, moving vast quantities of heat from low latitudes to high ones. It is the reason London, sitting at roughly the same latitude as the southern coast of Hudson Bay in Canada, has a temperate maritime climate rather than a subarctic one. It is the reason Norway remains habitable as far north as it does. It helps determine rainfall patterns across West Africa through its influence on the position of the tropical rain belt. The pump runs on density differences in seawater, and cold, salty water sinks. Both of the conditions that make this possible are currently changing. Warmer water is less dense, so it sinks less readily, and freshwater runoff from melting ice in Greenland and the Arctic dilutes the salinity in the regions where deepwater formation occurs, further reducing density. The result is a weakening pump. Evidence for this weakening has accumulated from enough independent sources that it is no longer seriously disputed. What remains genuinely contested is how quickly this weakening might unfold, and whether there is a critical threshold beyond which gradual weakening could tip into outright collapse. A statistical analysis of long-running Atlantic temperature records, published by a Danish research group in a leading climate journal in 2023, interpreted certain patterns in the data as a possible early warning signal of an approaching critical transition. The publication generated significant pushback over its statistical methodology, but the fact that such an analysis was published and taken seriously by the broader research community is itself telling. Since a decade earlier, most specialists would have considered a meaningful AMOC weakening within this century unlikely. A substantial weakening, not necessarily a full collapse, but a significant slowdown, would mean winter temperatures across Western Europe dropping several degrees relative to current conditions, an almost paradoxical regional cooling against a backdrop of global warming. Rainfall patterns across West Africa and parts of South America would shift, and sea level along the eastern coast of North America would rise further, because the circulation currently maintains a slight slope in the Atlantic surface that its weakening would remove. None of this represents instantaneous catastrophe, but together it represents a substantial reorganization of climate conditions across some of the most densely populated regions on the planet. This story has a hydrological counterpart playing out in the world's largest mountain ranges. The Himalayas, the Karakoram, the Pamirs, the Andes, and the Alps all contain glaciers that have functioned for millennia as natural water reservoirs, accumulating snow and ice in winter and releasing meltwater gradually through summer, feeding rivers that supply agriculture, cities, and hydropower for billions of people. Glaciers are melting, which is not news in itself. What matters is the dynamics of that melting. In an early phase, summer stream flow can temporarily increase as more ice melts, a phase sometimes called peak water abundance. And some river basins are already experiencing elevated flood risk because of it. But this phase has a natural endpoint. Once a glacier's accumulated volume shrinks below a critical level, summer stream flow begins declining, precisely when irrigation demand is highest. For a number of basins fed by Himalayan glaciers, published estimates suggest this peak has either already passed or will arrive within 2 to 3 decades. The Indus River, on which Pakistani irrigated agriculture depends to feed more than 200 million people, draws a significant share of its summer flow from exactly the glaciers now approaching this threshold. Alongside this, the basic structure of mountain precipitation is shifting as warming pushes more winter precipitation to fall as rain rather than snow, producing winter flooding while reducing water available later when it is needed most. The seasonal buffer is being eroded from both directions at once. The world's oceans absorb roughly a quarter of all human-generated carbon dioxide emissions, an enormous and largely uncelebrated service performed by the physics and chemistry of seawater. Without this absorption, atmospheric carbon dioxide concentrations would already be considerably higher. But this service carries a cost. When carbon dioxide dissolves in seawater, it forms carbonic acid, raising the concentration of hydrogen ions, a process known as ocean acidification. Since the start of the industrial era, average surface ocean pH has fallen by roughly 0.1 units. That sounds small, until you remember that pH is a logarithmic scale, so a 0.1 unit drop corresponds to roughly a 26% increase in hydrogen ion concentration over a century and a half. For organisms that build shells and skeletons from calcium carbonate, mollusks, sea urchins, corals, and a vast range of plankton, this shift means building protective structures requires more biological energy. And at sufficiently high acidity, calcium carbonate can begin actively dissolving. Tiny marine snails, known as pteropods, an important part of polar and subpolar food webs, have shown measurable shell dissolution in waters around Antarctica in recent studies. This matters beyond the individual species, because pteropods carry carbon toward the deep ocean when they die and sink. Fewer pteropods means less carbon reaching long-term storage on the seafloor, leaving more available to potentially return to the atmosphere. Coral reefs sit at the intersection of ocean warming and ocean acidification, and they illustrate the synergy between the two with unusual clarity. Reefs occupy less than 1% of the ocean floor by area, yet they provide habitat for roughly a quarter of all known marine species. They function as natural breakwaters protecting coastlines, and they form the basis of fisheries that hundreds of millions of people in tropical regions depend on. In 2023 and 2024, the world experienced a global coral bleaching event, recognized by international monitoring organizations as the most extensive on record, with damage spanning reefs across all three tropical oceans simultaneously. This is a direct consequence of the same abnormal ocean surface temperatures already described. When water temperature exceeds a critical threshold for the microscopic algae living symbiotically inside coral tissue, the algae are expelled. The coral loses its primary food source, turns white, and begins starving. If temperatures return to normal quickly enough, some corals can recover. If not, they die. The scale and synchronization of the 2023 to 2024 event across the entire tropical belt indicates this is not a regional anomaly, but a genuinely global phenomenon tied directly to overall ocean surface warming. Reef ecosystems that developed over thousands of years can collapse within a few decades. Recovery from a serious bleaching event typically takes 10 to 15 years under favorable conditions. If events of this scale recur every few years instead, recovery simply does not have time to occur. Tropical forests, the Amazon basin, the Congo basin, the forests of Southeast Asia function as more than reservoirs of biological diversity. They are active components of the climate system in their own right. The Amazon is a particularly striking case because it generates a meaningful share of its own rainfall through a process sometimes called the biotic pump. Trees release water vapor through their leaves. That moisture condenses into clouds. The clouds drift with prevailing winds and fall as rain hundreds of kilometers further inland, and the cycle repeats, carrying moisture progressively westward across the continent and sustaining humidity in interior regions that would otherwise be considerably drier. This is itself a feedback loop. The forest generates rain, and the rain sustains the forest. While intact, the system is self-stabilizing, but it has threshold behavior built into it. The combination of deforestation and intensifying drought has already pushed the southeastern Amazon, according to satellite monitoring data, into functioning as a net source of carbon rather than a net absorber. A qualitative shift for a region that had served as one of the planet's largest carbon sinks for centuries. If deforestation and drought intensification both continue, the point at which the biotic pump begins failing across much larger areas draws closer. A transition of substantial portions of the Amazon toward a savanna-like state is not a speculative scenario confined to worst-case projections. It is discussed in serious scientific literature as a plausible outcome of crossing several threshold characteristics of the system simultaneously. Boreal forests add their own troubling dimension. Warming initially looked beneficial there, a longer growing season, an expanding range pushing northward. But that benefit has proven temporary and, in important respects, illusory. Warmer, drier summers mean more intense wildfires, and area burned records have been set repeatedly in recent years. Fires in boreal regions carry particular significance because of the peat soils beneath them, meters-deep accumulations of organic material built up over millennia. Burning peat releases enormous quantities of carbon and is extraordinarily difficult to extinguish. Insect outbreaks compound the problem, as bark beetles, once kept in check by harsh winters, now complete multiple generations per season in some regions and can kill enormous stretches of forest within a few years. Dead trees become dry fuel, and the loop closes. Warming enables pests. Pests kill forest. Dead forest burns. Fires release carbon. Carbon drives further warming. Atmospheric methane concentration has risen roughly 2.5 times above pre-industrial levels, a faster relative increase than carbon dioxide has experienced. After a period of relative stabilization in the early 2000s, methane growth resumed and accelerated starting around 2007, and the elevated growth rate has persisted in recent years. Why this is happening remains an area of active scientific debate, and an honest answer is that the full picture is not yet settled. Several contributing factors appear to play some role. Rising biogenic emissions from tropical wetlands under warmer, wetter conditions. Expanding livestock production. Leaks from oil and gas infrastructure that satellite measurements have shown were systematically underestimated by ground-based reporting. And a more troubling possibility, a growing contribution from thawing permafrost. The isotopic composition of atmospheric methane can, in principle, distinguish thermogenic methane from fossil fuel deposits, from biogenic methane from wetlands or permafrost. But distinguishing wetland methane specifically from permafrost methane through isotopic signatures alone is extremely difficult, since the signatures partially overlap. If permafrost has begun contributing meaningfully to rising atmospheric methane, that represents exactly the kind of feedback loop that complicates any forecast. Because permafrost methane release does not depend on what humanity chooses to do with its own emissions going forward. Marine methane hydrates add a further layer of uncertainty. Solid, crystalline structures on the seafloor in which methane molecules are trapped within a lattice of water molecules under high pressure and low temperature. They remain stable as long as the surrounding water stays cold. If it warms, hydrates can destabilize. On shallow Arctic continental shelves, researchers have documented increasingly intense methane bubble plumes rising from the seafloor. Whether this represents the beginning of significant destabilization or simply variation within natural background levels remains genuinely unresolved. But the intensifying scientific attention to this question suggests it is not regarded as a minor concern. Most conversations about atmospheric change focus on temperature, rainfall, and sea level. Air quality receives far less attention, despite being one of the most direct and immediate ways atmospheric conditions affect human health daily. Climate change affects air quality through several simultaneous pathways. The first runs through wildfire smoke, which can travel 1,000 kilometers or more from its source, carrying fine particulate matter smaller than 2.5 micrometers in diameter, small enough to penetrate deep into the lungs and pass into the bloodstream. The link between this kind of exposure and worsened asthma, cardiovascular events, and developmental effects in children from prolonged exposure is well documented, and smoke events spanning entire subcontinents have become considerably more frequent in recent years. A second pathway runs through photochemistry. Higher temperatures accelerate the reactions that produce ground-level ozone, which, unlike the protective ozone layer in the stratosphere, is a pollutant at ground level, toxic to the respiratory system and damaging to vegetation. Hot, stagnant weather, becoming more common as circulation patterns shift, creates ideal conditions for it to accumulate. A third pathway runs through lengthening pollen seasons, as plants release pollen earlier in spring and later into autumn, directly increasing the duration of allergen exposure. A fourth, less obvious pathway runs through fungal pathogens, since warmer, more humid conditions in a number of regions favor the growth and spread of certain fungal diseases, with the range of some previously confined to particular climate zones now expanding. None of these consequences require a single dramatic weather catastrophe. They unfold gradually, embedded in the ordinary daily experience of breathing. There is a basic physical law underlying much of this, the Clausius-Clapeyron relationship, which establishes that the atmosphere's capacity to hold water vapor increases by roughly 7% for every degree of warming. This is not a model interpretation or a statistical inference. It is thermodynamics. Warmer air holds more moisture, and the consequence for the broader water cycle follows directly. When rain falls, it carries more water than it once did. Not necessarily more often, but more intensely per event. At the same time, during dry stretches in continental mid-latitude regions, higher temperatures accelerate evaporation from soil, drying it out faster and intensifying drought conditions. The result is a paradox that often confuses people hearing about floods and droughts in the same breath. In a world with a more intense water cycle, there is simply more of both, occurring in different places and at different times, with the extremes growing on both ends simultaneously. Data from recent decades supports this. The share of precipitation falling in short, intense events has been rising. The share of time the same regions spend in severe drought has also been rising. Not in the same places at the same time, but globally, on average, across the planet. For agriculture, this has concrete consequences. Intense, short-duration rainfall replenishes groundwater far less efficiently than steadier, moderate rainfall, because water runs off the surface before it has time to soak in. If the following month turns dry, soil moisture reserves end up lower than they would be under the same total seasonal rainfall delivered more evenly. Agricultural systems were optimized around a particular precipitation regime. When that regime shifts, those systems begin failing, not catastrophically in a single season, but steadily, with an increasing frequency of disruptive events. Monsoon systems, including the South Asian and West African monsoons, are particularly exposed in this context because they are driven by thermal contrasts between a warming landmass and the relatively cooler ocean, or the reverse, depending on the season. As that contrast shifts due to uneven warming of land and sea, the monsoon's driving force shifts with it. Observational data over the past 2 decades shows the Indian monsoon displaying increasing temporal and spatial irregularity alongside a rising intensity of individual rainfall events. Less predictability paired with more variability is a genuinely difficult combination for an agricultural system feeding well over 1 billion people and historically calibrated around a fairly consistent seasonal rhythm. Let's go back to the atmosphere, but to its outermost reaches this time, far above where weather happens, in the region where low-orbit satellites operate, a place where surface changes might seem to have no bearing at all. That assumption turns out to be wrong. The thermosphere, extending from roughly 90 to 500 kilometers above the surface, has become an unexpectedly sensitive indicator of conditions in the lower atmosphere. It is cooling, not warming, even as the layers below it warm. This is not a contradiction. It is a predicted consequence of the same greenhouse mechanism driving surface warming. A stronger greenhouse effect near the surface means more heat is trapped down low and less escapes upward. So the upper atmosphere, previously warmed in part by that outgoing radiation, now receives less of it and cools. This specific signature, a warming surface paired with a cooling upper atmosphere, was predicted decades before it was clearly observed, and it differs from the pattern increased solar activity would produce, which would warm the atmosphere more uniformly across altitude. A practical consequence of thermospheric cooling is reduced atmospheric density at low orbital altitudes, which directly affects satellites. Lower density means less aerodynamic drag, allowing satellites and debris fragments to remain in orbit longer without naturally decaying. This sounds beneficial for satellite operators, but it creates a genuine problem for space debris management. Fragments from defunct spacecraft that would once have re-entered and burned up within a certain time frame now linger in orbit considerably longer. The total population of objects in low orbit continues to grow, and the risk of a cascading collision event, sometimes called Kessler syndrome, increases correspondingly. It is a genuinely unexpected pathway through which changes in the climate near the surface end up influencing the safety of activity in space. No honest account of atmospheric change is complete without a discussion of how well our instruments and models actually capture it. Climate models rank among the most complex computational systems humanity has ever built to describe a natural phenomenon. Dividing the atmosphere and ocean into millions of grid cells and incorporating hundreds of parameterized processes representing decades of collective work by thousands of researchers. Despite that sophistication, these models have systematically underestimated several observed changes: the rate of Arctic sea ice loss, the magnitude of deep ocean warming, and the intensity of certain extreme weather events. Across these categories, reality has consistently landed in the upper portion of the modeled range, or beyond it entirely. This does not mean the models are poorly built. It means the underlying system is more complex than current parameterization techniques can fully capture. The problem has several layers. The first involves processes smaller than a single grid cell: convection, cloud formation, turbulence, described through approximate formulas whose choice meaningfully influences the outcome. The second involves interactions between subsystems, since nonlinear interactions between simultaneous factors are poorly captured by simply adding their individual effects together. The third is the training data problem itself. Models are calibrated against historical observations, and if the system enters a regime not represented in that record, reliability degrades exactly where accuracy matters most. This is part of why several leading climate research institutions announced significant revisions to their modeling platforms in the mid-2020s. Not simple parameter updates, but structural changes, with some moving toward hybrid architectures that apply conventional physical equations where the underlying physics is well established, and incorporate machine learning specifically to represent the nonlinear interactions where traditional parameterizations have produced systematic errors.
Neural network weather forecasting models that emerged in the early 2020s proved competitive with, or faster than, the best traditional physical models, a meaningful advance that carries an important limitation. These tools are trained on historical data and describe statistical patterns drawn from the past. So if the atmosphere has entered a regime not represented in that training data, a neural network will be least reliable exactly where precision matters most. Extrapolating beyond the boundaries of a training distribution is a fundamental limitation of machine learning as a method. Physical models at least remain anchored to conservation laws that hold regardless of which regime the system currently occupies, which is why a hybrid approach appears most promising, preserving physical grounding where physics is reliable, and drawing on the flexibility of machine learning, specifically where conventional parameterizations have repeatedly fallen short. In public discussion of climate change, the word adaptation often carries an optimistic undertone, as though it offers a comfortable answer to anxiety about the future. We will adapt. Humanity has always adapted. This is true, and it is not the complete truth. Adaptation is real and necessary, but it has limits defined by physiology, economics, and the timescales over which change unfolds. The physiological limit is the most fundamental. The human body cools itself primarily through sweat evaporation, and the efficiency of that process depends heavily on humidity. When temperature and humidity are both high enough that sweat evaporation can no longer provide adequate cooling, the body overheats. There is a specific physiological threshold, a wet bulb temperature around 35 degrees Celsius, beyond which a healthy person, resting in the shade, cannot survive without active cooling assistance. Calculations published in peer-reviewed literature indicate this threshold has already been briefly exceeded at several locations across the Middle East and South Asia. These episodes remain rare for now. At higher background temperatures, they will become routine across tropical and subtropical regions during the hottest months. There is no infrastructure solution that scales to an entire population for this threat. Air conditioning helps those who have access to it and reliable electricity. But for hundreds of millions of people in the hottest regions of the planet, that access simply does not exist. The economic limit follows close behind. Adaptation costs money. Raising levees, rebuilding irrigation systems, reinforcing buildings against extreme wind, relocating coastal communities, building water reserves. All of this is achievable, and wealthy countries have been doing versions of it with some success. But the pace required and its cost exceed the capacity of many of the most exposed nations. The regions that contributed least historically to accumulated greenhouse gas emissions
tend to bear the largest share of physical consequences, while having the fewest resources for adaptation. Sub-Saharan Africa, small island nations in the Pacific, the river deltas of South Asia sit consistently at the front of this exposure. The time limit closes the loop. Adaptation requires time to design, finance, and build. Infrastructure is typically designed with a planning horizon of 50 to 100 years. If climate conditions change faster than infrastructure can be updated, the gap widens continuously. Drainage systems overwhelmed by rainfall beyond design specifications. Bridges facing loads they were never engineered for. Transmission lines sagging under heat outside their original tolerances. None of these are catastrophes individually. They represent a steadily widening gap between design standards based on the climate of the past and the operating conditions of the climate of the present. Adaptation is necessary, but it does not remove the need to limit the underlying changes themselves. There is something the scientific community has increasingly begun discussing openly: a problem with language itself, with how these changes are described to the public. Scientific tradition demands careful phrasing, explicit acknowledgement of uncertainty, and probability ranges rather than absolute claims. Not timidity, but intellectual honesty. Science deals in probabilities, not certainties, and uncertainty is not a weakness in communication. It is an accurate description of the actual state of knowledge. But in practice, this tradition has produced an unintended effect. Uncertainty has often been misread as ignorance, and ignorance has been used by some as grounds for delaying action, even when the underlying disagreement was never about basic facts, but about precise numbers and timing. When 5 atmospheric subsystems simultaneously cross the boundaries of their documented historical variability, describing that with language like, "There exists a basis for believing observed changes may indicate the strengthening of certain trends," is technically accurate, yet inadequate as a vehicle for conveying actual meaning. A growing number of leading climate scientists have begun advocating for more direct, concrete risk communication in recent years. Not exaggeration, but a vocabulary genuinely calibrated to what the data actually shows. There is one more dimension worth stating clearly: the distinction between worse and different. The climate system is not moving toward worse in any moral sense. It is moving toward a different state, physically different, functionally different. For a civilization built around the relative stability of the past several thousand years of climate, that different state represents enormous costs and risks. But the atmosphere itself is not doing something wrong. It is changing the rules under which our systems were designed to operate. And understanding precisely what is changing and why is the first precondition for an adequate response. Why, given everything described here, do human institutions respond with such persistent delay? This deserves a genuinely honest answer, with several distinct layers. The first is cognitive. The human brain did not evolve to assess threats unfolding across decades. We are optimized for responding to immediate dangers: a predator, hunger, an acute conflict, not slowly building risks with probabilistic outcomes and diffuse origins. The second is economic. The benefits of fossil fuel use are concentrated and immediate. The costs are distributed across time and geography, materializing later, somewhere else,
affecting other people, or sometimes the same people, in a future that registers psychologically as an abstraction. The classic structure of a collective action problem. The third is institutional. Political institutions are generally optimized around electoral cycles spanning a handful of years, while the climate problem extends well beyond that horizon, creating a structural representation gap in which future generations have no voice in decisions made on their behalf today. The fourth is informational. The complexity of scientific description, dense with technical terms and probability ranges, creates psychological distance between the data and the decisions that data should inform. Probably, possibly. Under certain conditions, these are all accurate descriptions of the actual state of knowledge, but they also provide convenient cover for anyone motivated to ignore the underlying risk. Understanding these mechanisms is not grounds for fatalism. On the contrary, only by understanding why institutional response lags can anyone work meaningfully to address the specific elements producing that delay. Carbon markets attempt to make the cost of emissions more immediate and visible. Climate risk disclosure requirements attempt to embed climate factors directly into financial decision-making. International agreements attempt to build coordination mechanisms where national incentives alone are insufficient. All of this moves more slowly than the physical system demands. The gap between the emissions trajectory the world is currently on and the trajectory implied by current commitments remains significant. But there has been measurable progress, even if it has not yet closed that gap. What concretely can be done with this understanding? Reducing greenhouse gas emissions remains necessary. This follows directly from physics rather than from any side of a political argument. The less carbon dioxide added going forward, the smaller the eventual scale of change, and the more time available for natural and human systems to adapt, regardless of where the system currently sits on the spectrum between an intensifying trend and a full regime shift. But if the possibility that the system has already crossed, or is closely approaching, several threshold characteristics is taken seriously, additional tools deserve consideration. One frequently discussed option is solar geoengineering, deliberately introducing reflective aerosols into the stratosphere to mimic the temporary cooling produced by large volcanic eruptions. This is technically feasible, and the underlying principle is well established, but it is not a solution to the underlying problem. At best, a way to buy time. If aerosol introduction stopped, temperature would rapidly return toward its previous trend, and side effects, changes to rainfall, disruption of monsoon systems, could be substantial and unevenly distributed. Managing such an intervention would require a level of global coordination humanity has no real precedent for achieving. Large-scale ecosystem restoration and protection, forests, peatlands, mangroves, seagrass meadows, functions simultaneously as a carbon storage mechanism and as a means of preserving biogeochemical feedbacks that themselves contribute to climate regulation. Rethinking the pace of aerosol pollution removal matters too. The shipping fuel episode demonstrated that rapidly eliminating an unintentional cooling effect is itself a form of climate forcing. So transition strategies should account not only for emissions reductions, but also for the loss of cooling effects that have, until now, accompanied dirtier fuels. Substantially improved monitoring matters as well. Blind spots in the global observation network, across the open ocean, at great depth, in the upper atmosphere above sparsely populated regions,
means some changes are detected with significant delay, and a denser, smarter observation network is not a luxury, but early warning infrastructure. None of these directions are simple, and none are sufficient on their own. All of them demand a level of seriousness considerably beyond what current institutional response speed has demonstrated so far. Let's return to where this conversation began, to the robotic float drifting somewhere in the Southern Ocean, recording a value that had never appeared before. That single measurement took its place within a much longer record, one that, taken as a whole, sketches a picture of the planet's atmospheric and oceanic state, a picture science is reading with increasing precision even as it continues delivering surprises with a frequency that seems to rise the more closely the system is observed. This is not evidence of scientific failure. It is evidence of the underlying object's complexity. Earth's atmosphere is, quite possibly, the most intricate physical system the human mind has ever attempted to describe. It is nonlinear. It spans scales from individual molecules to planetary-scale waves, and it is embedded within other complex systems: the biosphere, the hydrosphere, the solid Earth, with which it constantly exchanges energy and matter. It has existed for more than 4 billion years and has accumulated a depth of behavioral complexity that exceeds any single model's capacity to fully capture. The fact that our understanding remains incomplete is not a reason for resignation. If anything, that very incompleteness is precisely why caution is warranted. Driving through fog, you do not accelerate simply because you assume the road ahead is straight. Complex systems do not reliably announce their transitions with convenient, well-timed warnings. They change according to their own internal logic, a logic indifferent to human calendars and institutional planning horizons. And scientists generally describe these changes only after they have already occurred, because there is never quite enough data, and what data exists always arrives somewhat late. That is precisely what appears to be happening right now. The atmosphere has done something without precedent in the documented observational record. Several key parameters crossing the boundaries of their known range at the same time. Science has registered this, described it, and begun to understand it. The mechanisms responsible have not switched off. They continue operating. The accumulated momentum of changes already set in motion is not going anywhere. The cryosphere will continue losing mass. Permafrost will continue thawing gradually. The water cycle will continue intensifying at its extremes. These outcomes are already embedded in the system, but the scale of what happens next is not predetermined. The difference between possible future trajectories is a real difference, measured in meters of sea level rise, in the area of degraded ecosystems, in the number of people experiencing physiologically extreme heat. That difference will be determined not through surrender or panic, but through technological, political, and institutional decisions made here and now, by people who understand what is actually happening. Understanding comes first. The atmosphere above you right now is the same gaseous envelope that has held liquid water and a habitable surface temperature on this rocky planet for roughly 4 billion years. It survived the asteroid impact that ended the age of large, non-avian dinosaurs. It survived the largest volcanic episodes in the planet's history. It survived ice ages and the warm interglacial periods between them. It is resilient. But resilience is not the same as immutability.
It describes the capacity to persist in a given state until a disturbance exceeds the threshold required to push it into another one. And we may now be, for perhaps the first time in the history of life on this planet, a geological force capable of moving that threshold closer or further away through our own collective decisions. A conversation about the atmosphere, in that sense, is never really a conversation about science in isolation. It is a conversation about what we choose to do with the understanding science provides us. The atmosphere did something that had never happened before. And this is only the beginning of the conversation about what happens next. Every year, as winter settles over the southern hemisphere, a vast stratospheric vortex begins forming above Antarctica, spinning up slowly, gathering strength, holding the cold in place over the pole before unwinding again as spring approaches. This cycle has repeated for thousands of years. In January 2022, while that vortex was still months away from forming, an underwater volcano thousands of kilometers to the north exploded, with a force barographs around the world recorded multiple times as its shockwave circled the planet. Its plume rose higher into the stratosphere than any eruption in the modern instrumental record, and it carried with it something the stratosphere had never held in such quantity: water. That water began interacting slowly with everything around it, warming a layer that had previously been transparent to outgoing heat, interfering with chlorine chemistry, altering the conditions under which planetary waves propagate, gradually sinking into the troposphere and reinforcing high-altitude cloud cover along the way. At nearly the same time, new international rules for marine fuel took effect, and as ships across the world switched to cleaner fuel, the pale reflective trails that had quietly shaded stretches of open ocean for decades began fading. Darker water absorbed more sunlight. Two events, one geological, one a direct consequence of a deliberate human decision made for entirely sound reasons, landed on a system already under strain. A shrinking temperature contrast between the tropics and the Arctic, a weakening and increasingly erratic jet stream, and a deep, accumulated thermal debt stored in the ocean. A nonlinear system did not simply add these two disturbances together. It multiplied them through its own internal mechanisms. The result is what instruments recorded across 2023 and 2024, a simultaneous departure of several independent parameters from the boundaries of their documented historical range. The mechanisms behind that departure have not switched off. They continue operating. The water cycle continues intensifying. The Arctic continues warming faster than the rest of the planet. The jet stream continues meandering. Glaciers continue retreating. Permafrost continues thawing. Coral reefs continue bleaching. Atmospheric carbon dioxide continues accumulating. A robotic float somewhere in the Southern Ocean continues recording. Science continues working, not in a straight line, with disagreement, with revision, sometimes with uncomfortable findings, because that is how science actually functions, not as a finished catalog of settled answers, but as a continuous process of refining and understanding of a reality that is always richer than any single model of it. The atmosphere above you, right now, is a living machine that has been running for nearly 5 billion years. It has never stopped. It will not stop now. It will keep doing what it has always done, redistributing heat, generating weather, exchanging energy and matter with the ocean, the land, the biosphere, with sunlight, and with the darkness of space beyond. Only now, slightly differently
than before. And slightly is, in many ways, the most important word in this entire account. Because in a complex, nonlinear system, a small shift at the level of mechanism can produce a fundamentally different outcome at the level of result. We appear to be living through the moment when that fundamentally different outcome moves from a theoretical possibility into a measured reality. The instruments are showing it. The science is describing it. What happens from here rests with the people capable of reading what those instruments show and choosing what to do with what they read.